Okay, so we're gonna move on to our next topic, which is simple harmonic motion. Example of that is a mass moving back and forth in a spring, back and forth and back and forth and back and forth. Now, the forces that act on it are normal force and weight, and then the spring force, which according to Hooke's law is K times the extension. This point here is the zero, it's the equilibrium point, and with the mass located at position X, there's a Kx force. So if we apply Newton's second law, sum of the forces is Kx. Well, it's always going to be Kx opposite of X. So right now you can see the forces to the left. So that would indicate that's what the negative reflects. That's going to equal the mass times the acceleration, but of course the acceleration is the second derivative of position, so we arrive at this differential equation. X double dot is minus k over m times x. So we need a function x, the position x will be such that when you differentiate it twice, you get itself times a constant. So which function equals its own second derivative? Well, from Cal 1, you probably know that if you differentiate cosine, you get minus sine, and if you differentiate minus sine, you get back to cosine. So this is a good candidate solution. A cosine omega is just some constant times t. So let's try that. Let's put a cosine omega t in for x. Now, if we differentiate that once, we're going to get minus a sine. But then, of course, by the chain rule, we have to multiply by the derivative of that argument. And the derivative of omega naught t is just omega naught. So the omega naught comes out. And that is the first derivative of position. The second derivative of position, we differentiate again. And the derivative of sine is cosine. But then, of course, by the chain rule, you multiply by the derivative of the argument. There's another value, there's another term in omega naught, so now we've got omega naught squared. So if we compare that then, we can see that our second derivative of our test function here was minus a. Oh, let me just rearrange that a tiny little bit, because I'll just pull the omega naught squared out in front. And then it's a cos of omega naught t. Then on this side, we got negative k over m, and then we'll put in the x function, which was a cos of omega naught t. So we could see that the a cos omega t appears on both sides. So this will be a solution as long as the omega naught squared equals k over m, or as long as omega naught is the root of k over m. And that should be familiar from your previous study of simple harmonic motion in first year physics. Now, cosine omega t is just one solution. You can also show that sine is another solution, and a second order differential equation, which has a second order derivative of x, is going to have two independent solutions. So the general solution is going to involve a sum of both sines and cosines with some unknown amplitude d1 and d2. Now that can always be combined together and written in the form a cos omega t plus delta. The main thing is that there's two parameters. Here the two parameters are d1 and d2. Here it's a and delta. So these are two ways of writing the solution to the simple harmonic oscillator. Now, if we use that second form, then we can find an expression for the velocity just by doing the derivative. We did that earlier. We know that it's going to be minus a omega naught comes from the chain rule, sine of omega naught t plus delta. And then we can work out the energy here, the kinetic energy plus the potential energy, and show that it's a constant. Now the potential energy is 1/2 kx squared. And then this is x. And so we're going to do 1/2 mv squared plus 1/2 kx squared. So this is the velocity function right here, minus a omega naught sine of this argument. And then the x is a cosine of that same argument. Now you have to include your definition of omega naught, but then you can show that total mechanical energy is indeed conserved for this motion. And your assignment problem is just to do that. So now let's do a first year physics problem. Let's find the equation of motion. Position is a function of time. Here we've got a mass moving back and forth on a spring. It's on a frictionless surface, and initially the mass starts out over here, 0.3 meters from equilibrium, and it starts out at rest. So you're going to let this go, and it's going to go back and forth, back and forth, back and forth, 30 centimeters either side of equilibrium, so clearly the amplitude is just 0.3 meters. Now the rate of vibration omega is root of k over m. K is given as 20. The mass is given as 200 grams or 0.2 kilograms. So we have 10 radians per second, root of 100, for the rate of vibration. So then the other thing we need, of course, is the initial phase. Now in this equation of motion we're using, so we found the amplitude. It's 0.3. We know the rate of vibration. So if we can substitute in a value of x and t, then we could solve for delta. Well, we'll substitute in the initial condition. Okay, so we'll put in then the amplitude is 0.3 cosine 10 times t plus delta. So we're going to put in a time of 0 and an initial position of 0.3. So that's the x value, that's the t value. So 10 times 0 is just 0, so we're just left with cos delta here. And then we divide both sides by 0.3 and you get 1. So delta is the inverse cos of 1, which is 0, 2 pi, etc., etc., etc. Those are the same angles, so we can see that without loss of generality, we just can take 0. So we've got then an expression for the position as a function of time, just 0.3 cosine 10t. Now, let's take the same original condition. You've got the same mass, the same spring, the same distance from equilibrium, except now we change things, and this mass, the initial condition, isn't at rest, it's actually moving. It's going 0.4 in the positive I direction. So clearly it's going to go a little bit further before it stops and then turns around and goes back to the other side. So that means we can no longer get the amplitude by just inspection. It's not just going to be 0.3. We can use energy conservation, right? We could say that initially it's moving and there's some elastic energy in the spring. When it moves over here and comes to rest, there won't be any more kinetic energy. It'll just be elastic energy. And at that point, the spring will be stretched by an amount A, which is the amplitude. So we could substitute in then the values, the mass of 0.2 kilograms, the speed here of 0.4 meters per second squared, the k value of 20, the initial distance from equilibrium of 0.3, the k value of 20, and then we could solve for the amplitude of motion. Now it's not a lot bigger than 3, but I'm just going to keep a few sig figs here, an inordinate amount of sig figs for our next calculation. Now, omega is the same as before. That's still going to be 10 rads per second because it's the same spring and same mass. But then for the initial phase, we've got our initial condition here. At time 0, the position's 0.3. However, it's not at rest. We have a different amplitude this time. So, oh, it was right here, sorry. So, okay, so for our initial condition then, we're starting at plus 0.3 when the time is 0. And I'm just going to keep a lot of extra sig figs there just for accuracy. So there's the amplitude. Omega naught is 10. Of course, the time is 0. And, oh, I forgot the cosine. Yeah. Okay, let's just do that again. Okay, so cosine of 10 times 0 time plus delta. So we substituted in the initial condition for position and time. And now, oh my goodness, what a disaster. We got to put in the correct amplitude there. But it's not a disaster, it's just a waste of time. So this was 0.30265 cosine 10 times 0 plus delta. So one final time, we would divide this over and then do the inverse cosine. Now when you do that, okay, it's the cos inverse of 0.3 over what this amplitude was. And for a reference angle, you get 0.132 rads. But of course, there's two solutions to that equation because cosine is positive here, but it's also positive over here in quadrant 4. And the other solution is 2 pi minus the reference angle. So if you do 2 pi minus this one, you get 6.15 rads. So those are two distinct angles, and we need to know which one. We're going to look at the velocity function here to discern which one's correct. If we had the quadrant 1 solution, the sign would be positive at time 0, and then because of this negative, we would get a negative initial velocity. But because we have positive initial velocity, it's got to be the quadrant 4 solution. If I put in time 0 at a quadrant 4 angle, this whole thing's in quadrant 4. The sign will be negative, and a negative times a negative is indeed a positive one. So this one gives the correct initial condition for position and velocity. So we can now conclude, and now I'll drop a few sig figs. We can now conclude that our initial phase must be 6.15 rads, and that is the position as a function of time for that second case where the mass was initially moving. So those are some typical first-year physics problems related to simple harmonic motion. Now we want to up the ante a bit in terms of the differential equation. Here it is again. Now we'll remind ourselves that the variable omega naught is the root of km. So what we've got here is omega naught squared times x. If I then take that minus omega naught squared over the other side, it becomes plus omega naught squared. I'm going to make that look like a difference of squares by introducing the complex number I. I squared is minus 1. So I can replace the positive with negative I squared. And now it looks like a difference of squares. So we can factor that as, so this is like a squared, if you like. And then these two terms here are like b squared. So it's going to be a minus b times a plus b, where b is just I omega naught. So there it is right there. So that's a plus b, and then this is a minus b. Now both of those acting on the function x must be 0. Now these are really operators, but we can still factor them like this, as you'll see in advanced mathematics classes. Now, in order for those operators to act on a function of x and give it 0, the operators themselves have to be 0. Or they must operate on x individually and get 0. So either this one is 0 with the plus, or the other one, the ddt minus I omega naught acting on x, must be 0. So that just takes us down to an equation that's a little simpler to solve. So we then distribute the x over both terms in the operator. We get this. We bring this to the other side. And maybe I'll show that step there. Because what we do next is we separate the variables. We divide the x down and the dt up, and that gets this expression here, which we're then going to integrate. Now, this side here is a dt integral, so we're going to integrate it from an initial time of 0 up to a final time. This is a dx integral, so we're going to integrate from an initial position up to a final position. Now, the integral of dx over x is just ln x. And, oh, there it is, finally. So that's going to be ln x, but then you've got to substitute in the upper and lower limits. So it'll be ln x minus ln x naught, which is the ln of x over x naught if we skip a few steps. The integral of dt is just t. You put in the upper and lower limit, and it's just minus I omega naught t. Now, we are going to raise both sides to the power of e, which will undo the log function. And so here we'll get e to the minus I and omega naught t. So that's going to be x over x naught is e to the minus I omega naught t, and then we cross multiply. And so we get a term like this. So it's an exponential function with, depending on time, with our constant omega naught, but then it's got this complex number I in it. And this is kind of a new quantity for us. It turns out that these complex exponentials are everywhere in physics. So if this is your first exposure to it, then it's certainly not going to be the last. Now, of course, we had the other equation that we didn't solve, and that's just going to yield pretty much the same result, just with a plus I omega t. And so if we put those two independent solutions together, you'll get something of the form. Let's see if it's here somewhere. Nope, where did that go? Where was that? I think I saw it. Nope. I thought I saw it. Okay, so you'll get something. Okay, so the pages were just out of order, but yes, right here, so this is what I was looking for. So this is another way to write the general solution of the harmonic oscillator. Earlier we had it as a sum of a cosine and a sine, or as a cosine of omega t plus delta, but this is another perfectly valid way of writing it. Now, another way to arrive that is to go back to our original differential equation and just substitute an exponential function in and see what happens. Now, if this is your function here, if it's e to the alpha t, then we're going to differentiate that twice. Now the first derivative, when you do the derivative of the exponential, you get itself, but then times the derivative of the exponent, which is going to give you a term alpha in front. Then when you do the second time derivative, you'll get another alpha. It'll be something like this. So this side we've got alpha squared e to the alpha t. Here we've got minus k over m times the x function, which again we're letting just be e to the alpha t. So clearly those two are equal to each other, provided alpha squared is minus k over m, or alpha is the root of negative k over m. Now we split that into two parts, the root of negative 1 and the root of k over m. We realize that this is omega naught, and this is the complex number I. Now, of course, we've got it plus or minus here, plus or minus, plus or minus. And so that was our exponent of the exponential function. So we see it's going to be plus or minus I omega naught t. So again, we've come to that conclusion in just a different way by substituting this into the original differential equation and not factoring it as operators. We can see that once again that this is another way of writing the general solution to the harmonic oscillator. So that's really the first message for today, that this problem of the harmonic oscillator, the solution can be written in many ways: cosine omega t plus delta, cosine omega t plus sine omega t, and then this third and final way, e to the plus or minus I omega naught t, where omega naught is the root of k over m. And this I is the square root of minus 1. It's a complex number. Now, another important idea related to harmonic motion, by the way, just to realize that it's perfectly okay for a position to be given by a complex function, because of course complex functions have real parts and imaginary parts, and when it comes right down to it, we're just going to take the real part of the exponential whenever we want to describe the position function in meters. Now, the way to do that is to use de Moivre's theorem, which you're going to prove as an exercise. E to the I theta is cos theta plus I sine theta. So clearly this would be the real, and this would be the imaginary part of the complex exponential. Now you're going to prove that using Taylor's series. Now, a final idea here related to elementary harmonic motion, and this is a bit of a new one, is the idea of phase space. So we're actually going to plot speed on this axis and position on this axis. Now, because as you showed earlier, half mv squared plus half kx squared, that's the mechanical energy of the system, and that's a constant, then we've got this equation relating v and x, and something like this is actually the graph of an ellipse. Remember, sort of standard form for the ellipse is something like x squared over a squared plus y squared over b squared is 1, and that gives you an ellipse where this distance is a and this distance here is b. ends up being elliptical like that. Okay, now without knowing what this constant is, we can't scale the axes, but we can say that the graph is going to be an ellipse, and let's just draw it like this. And if we did know the values of position and the spring constant and the mass and this, then we could figure out which coefficient was larger, and the larger coefficient, well, that'll be the longer axis for the ellipse. Now, if we look at the problem we were just dealing with, where we're letting the mass go at positive a, then we can actually plot the motion in phase space, because we know we're actually starting here. And what happens next, of course, is that as the mass moves towards 0, the velocity increases and becomes a negative number. So on your plot, you're getting to smaller x, but the velocity is becoming negative. So we must actually be sweeping out this way on our plot. Then the mass goes to the other side to negative a, so that's over here. And so we're tracing this direction on our phase space plot. This is called phase space, because it just shows us the relative values of position and velocity. And if there's no friction, then we'll come right back to where we started, right? The same distance plus a from equilibrium, and just repeat that motion in phase space over and over and over again. Now this plot gets a little bit more interesting when we include friction, but what we're paying attention to here is the direction that it's moving in phase space, and also the shape. It's an ellipse, and that is required by the conservation of mechanical energy. So those are some initial considerations for harmonic motion.